So let's take a look at 5.5. This is, so far the only integration or the only anti-differentiation technique that we've got is recognizing the end result of a differentiation formula and then just realizing, oh, I just need to reverse that. We're going to cover the most commonly used integration technique today. And it's the only other technique that we cover in this class. In 1220, you go over a bunch of integration techniques. We only are going to learn two, recognizing the end result of a differentiation formula and what we're doing today called the substitution rule or integration by substitution. So what's the most commonly used differentiation tool? Chain rule, okay? So we use the chain rule all the time. So the chain rule says this: derivative of the outside, leave the inside alone, times the derivative of the inside. So if that's the most commonly used differentiation technique, that's the one that we're going to undo, okay? And we're going to undo it using the substitution rule. And noticing how we figure out the chain rule and what the chain rule looks like is the key to figuring out how to undo that. So when we do the chain rule, we've got this inside function that appears right here, and its derivative appears out there. So when we use the chain rule, we talked about why they call it the chain rule. They call it the chain rule because we see a bunch of functions and their derivatives that are all multiplied together. And that's the key to recognizing how to undo the chain rule. We're going to see a function and its derivative somewhere in here. So again, just practicing with the chain rule, if I find the derivative of this right here, well, I'd bring this down, so that's going to be the 5 times 1/5. In fact, let me write it like that. So I'd have 5 times 1/5, 1 plus x cubed. I reduce the exponent by 1. So that's the derivative of the outside. I've left the inside alone. And then I times it by the derivative of the inside. So I'm just looking at this inside function right here, 1 plus x cubed. Derivative of 1 is 0, and the derivative of x cubed is 3x squared. And then I clean up that mess just a little bit. These are going to cancel. And I normally write this out front, so I'm going to write 3x squared, 1 plus x cubed raised to the 4th. Okay, so that's the derivative. Okay, now, here's an indefinite integral. Now, if we just look at this indefinite integral, that says we need to find the antiderivative of this integrand right here. So how does doing this problem right here help us figure out this problem right here? How does doing the differentiation help us figure out the integration? Yeah, you just reverse it, okay? Now, if I had put this problem on the board first and said, hey, what's the antiderivative of this? We actually had one like this on the board the other day, and what we had to do is we had to distribute through. We had to square things or cube things or multiply them by themselves 4 times in this case, distribute through, and then use the power rule. Yeah. Well, I just happened to find the derivative of a function that has this as its derivative. So if I hadn't done this problem right here, there's no way we could say, oh, I recognize that. That is 1/5, 1 plus x cubed raised to the 5th plus c. There's no way we could do that. There's no way we'd be able to recognize that. And going through and differentiating tons and tons of functions just in the hopes that we run into one of those that is an indefinite integral isn't a very good idea. Okay? So we want to have a technique that makes this process of undoing a little bit easier to recognize. So this is called the substitution technique or the substitution rule. And sometimes we call this a U substitution. Now, you've actually seen substitutions before, or what we'll call a change of variables. And we use this quite often. And we do it when we see something that looks complicated and we want to make it look more familiar. In fact, if you had to generalize U substitutions, or a change of variables, we're making something that looks really complicated look much easier and much more familiar. You learned how to do substitution when you're solving trig equations. You make ugly trig equations look much more familiar. You learn how to do factor by substitution. You'll have some ugly, ugly mess of a problem, and you factor it by recognizing, oh, I can substitute this here, and then it just turns into a trinomial or something like that. So we're going to do this one using a substitution technique. So here's what we're going to do. We're going to change the variables. We're going to say u is equal to 1 plus x cubed. Now, this is called substitution or change of variables for a reason. We're going to do some substituting and we're going to change the variables from what they were in the original problem to something that will look a little bit more familiar. So wherever there's a 1 plus x cubed, I can put a u. So I'm going to write integral, and then I'm in parentheses, I'm going to put a u, and then this is raised to the fourth. Now the problem here is I've got to get rid of this 3x squared. I've got to write that in terms of u, and I've got to write the dx in terms of u. Well, with this equation right here, u is equal to 1 plus x cubed. Just like the regular rules of algebra, if I do the same thing to both sides, I get another true equation. So what if I differentiate both sides? Or find the differential of both sides would be a better way to say it. The differential of u is du. The differential of 1 plus x cubed is 3x squared dx, carrying out the chain rule. Remember when we did differentials? So this means wherever there's a 3x squared dx, I can put a du. So there's a 3x squared dx, so I can put a du in its place. So I've gone from this ugly mess right here to finding the integral of u to the fourth du. Now look at this. That again, the only reason that that looked even reasonably familiar is because we did that differentiation to begin with. I've gone from that ugly mess to this right here. So we can kind of blot out the rest of this. Let's not worry about that for the time being, and let's just stare at that for a second. That's a piece of cake. Yeah. Integrate the fourth power function. I'm going to increase the exponent by 1, so that's going to be to the fifth power. I'm going to divide by 5, or in other words, that's going to be a 1/5, and then I'm going to add c. Now that's not the answer to the problem, but that is the hard part. Integrating is the hard part. All I need to do is write the answer in terms of x's. So I made the substitution. I made the change of variables to x's, from x's to u's to make that look simpler. In order to write down the final answer, I need to reverse the substitution and write the final answer in terms of x's. So wherever there's a u, what am I going to put in its place? 1 plus x cubed. So this is 1/5. 1 plus x cubed raised to the fifth plus c, and there's the same antiderivative, but we didn't have to do the differentiation in order to recognize it first. Okay? Okay, that's the substitution technique. That's integration by substitution in a nutshell. Let's point out a couple of things. Okay, the 1 plus x cubed and its derivative appeared in the integrand. So you can see this function right here and its derivative in the integrand, and that, again, that's the key to noticing when we can use the substitution technique. Okay, so we've got to change all the variables so that they need to match. So we're going to exchange any expression from x to u, and we also have to change out the differential. So everything's got to be in terms of that new variable u, including du. So you can't mix variables. We couldn't leave the dx there. This has got to be a function of u and a differential of u. And later on, we're going to get to the point where even the upper and lower limits, when we do a definite integral, we're going to need to change those as well. Okay? Any questions there? So we're literally changing all the variables in the problem. Okay? So a couple hints here. When we use integration by substitution, we're going to use that when we can see a function and its derivative in the integrand. Or we're going to modify this just a little bit, or a constant multiple of its derivative in the integrand. And I'll show you why that's the case in just a minute. Okay, and it would be also good, a really good thing if we recognized what we're doing here. Integration by substitution undoes what rule? It undoes the chain rule. Okay? All right. Any questions? Okay, I'm going to do one more where I give you a bunch of help to begin with so we can kind of recognize what's going on. If we differentiated this function using the chain rule, I'd find the derivative of the outside. So that would be 7, 8 plus sine of x. I'd reduce the exponent by 1, so that would be 6. And then I'd multiply by the derivative of 8 plus sine of x, which is cosine of x. So this is hugely helpful in figuring this out. Okay. If I integrate this, I'm going to get right back to this guy right here, plus a constant, because it's an indefinite integral. Okay. So the answer to this problem, let me change colors here. The answer to this problem is going to be that function right there, 8 plus the sine of x raised to the 7th plus c. Okay, because we just did the differentiation and we can recognize that this is going to undo it because we're going to integrate. Okay, but now we want to do this using substitution. So usually we're going to look for the inside of a function to be u. Sometimes that can be difficult, what our choice of u is. So I'm going to let u equal 8 plus the sine of x. Now, you'll notice that what happens here is this is not only the inside of a power function, which gives us a good hint that it might be the u, but you can see the derivative of that function in the integrand. The derivative of 8 plus sine of x has a plain old cosine in it, and there's a cosine sitting right there as a factor. So you can see its chain in the integrand, if that makes sense. So we'll just double check here. Remember, we need to change everything. So not only do we need to change u's, we need to change into du's. So this is going to be cosine x dx. Yeah.
And the 7 doesn't matter, and that's what you were saying about the constant.
Yep, the 7 doesn't matter because it got there because of that power right there. So let's just go through and replace things. So wherever there's a cosine x dx, I'm going to put a du. So here's a cosine x dx. So in that place, I can put a du. Wherever there's an 8 plus sine x, I'm going to put a u. So this is going to be u raised to the 6th. And that 7 is fine sitting right there for several reasons. Constants are easy to deal with. Constant multiples are easy to deal with when we're differentiating. You kind of get to ignore them. And they're easy to deal with when we're integrating, because you can kind of ignore them and then just figure out what happens when we simplify after the fact. Everybody good there? Okay, but on this one, this is pretty sweet because if I rewrite this so it looks a little bit more familiar, the integrand is 7u to the 6th. Well, we differentiate all the time. We've differentiated power functions. That's one of the things you're going to remember 20 or 30 years from now. Okay? What function has a derivative of 7u to the 6th? U to the 7th. U to the 7th plus c. So we've gone from something that looks ugly and unfamiliar to something that looks very familiar, very easy integration. The only thing we need to do now is reverse the substitution, change the variables back to what they were originally. So this is going to be 8 plus sine of x raised to the 7th plus c, and notice how that matches up with what we got here, recognizing the end result of a differentiation, kind of a formula, really the end of result of a differentiation problem. Okay? So that 7 is there because of the differentiation of the power function. Let's take a look at this one right here. I've changed colors. We're going to run through and do this one. There are several reasons why that constant could be there. In that last problem, is that it was there because of the differentiation. Let's take a look at this one. Again, we'll notice that the 8 plus sine of x is the inside of a power function, giving us a hint that that might be u. U is usually the inside function. But also the fact that if you differentiate this, you can see its derivative in the integrand. So again, our choice is to have u equal 8 plus the sine of x. We need to replace the differential as well, so we'll differentiate both sides. So this is going to be cosine x dx. Okay, I'll color code this one. Wherever there's a cosine x dx, we're going to put a du. And wherever there's an 8 plus sine of x, we're going to put a u. Everything else is just a number, and I can deal with numbers. I can deal with them if they're powers, and I can deal with them if they're constants. So on this problem right here, well, let's take a look. So if I replace things, this is what I've got. I've got the 70. In place of the cosine x dx, I'm putting a du, so I'll put a du here. and that's just going to be u to the 6th. And then let's integrate. We can deal with the 70, right? So I'm going to increase the exponent by 1, divide by the new exponent. So that's going to be 70 u to the 7th over 7 plus c. So that's going to be 10 u to the 7th plus c. So why was this 70 instead of 7? Because there was a constant of 10 there, a constant multiple of 10 in the function to begin with. Okay? So this 7 is there because of the power rule. Okay? That 70 is there because of the power and because of that constant of 10 that was there to begin with. Okay? Again, we're done with the difficult stuff. Now all we need to do is just reverse the substitution. So this is going to be 10, 8 plus sine of x raised to the 7th plus c. There's our answer. How could you double check? Just find the derivative. And look, there's the 70 that we need. That would turn into a 6, leaving the inside being 8 plus sine of x. And then we'd find the derivative of 8 plus sine of x, which would be cosine of x. And there it is right there. Okay? All right. Any questions?
I thought it was a little faster to just take out a 10 from the very beginning.
Okay, so Juan thought it was easier to take out a 10, but you're not always going to spot that, and that's not always going to be the best thing to do. Okay? But you're right. On that one, it is easier. So Juan's just recognizing, gosh, this is just a multiple of 10 of that one right there. So let's slap a 10 in front of this. Okay?
Yeah.
Okay, but what's the problem with Juan's answer right there? Are we always going to do this problem before we do this problem? No. Okay? And in fact, that's what we're doing from now on. We're basically just going from scratch. There's not going to be any, this function relates to that function or anything like that. So let's take a look at this one right here. And this sentence right here, the constant multiple could have come from the outside function, another from that power, okay? Or it could have been the constant that was there to begin with, okay? So let's take a look at this problem right here. And we want to find the antiderivative here. There are a couple different ways you can do this. These two problems are actually, I think they were on the integral tables that I showed you in the last section. But we want to be able to figure these out from scratch. So we want to figure out, well, how did they come up with the integral table in the first place? And most of those were found using a substitution technique. So what would we use for u on this problem? Okay, so again, usually, not always, but usually the u is going to be the inside function. So if I say u is equal to 7x, and I change the differential as well, this is going to be 7 dx. Now let's take a good look here. I've got a 7x that I'm going to replace with a u, and I need to replace a dx, but I don't need a 7 dx. But this is an equation, right? So what could I do if I don't need that 7 there? I could divide by 7 on both sides, right? So I can use 1/7 du is the same as dx. So I'm going to replace wherever there's a dx, I'm going to put a 1/7 du. And wherever there's a 7x, I'm going to put a u. So this is what I'm replacing here. I'm changing this just slightly. So this is going to be the sine of u. And then this is a du, and I'm going to put a 1/7 out front here. If it makes you more comfortable, we could do this. And then it should really look familiar. Let's see. If you're differentiating sine, you don't put a negative in there. If you're anti-differentiating sine, you do put a negative in there. So this is negative cosine u, okay, with a 1/7 out front. So I'll just put that plus c. Does that work? So now if I replace the change variables back to the x's, this is going to be negative 1/7 cosine 7x plus c. And we could quickly double check ourselves. The derivative of cosine is negative sine. So I've got a negative and a negative. That would make a positive. So we're in good shape there. I leave the inside alone. So it's going to be the positive sine of 7x. Okay. times the 7, and the 7 would cancel with the 1/7. So is that the right antiderivative?
Yep.
Okay. Everybody see that? Any questions? Okay. Okay, we're starting off fairly easy. They're going to get pretty interesting here in a second. Let's take a look at this next one. Again, you could find this in an integral table. You could find the antiderivative of e to the k x or dx or something like that, and it would show you what it is. Let's reason our way through this using a u substitution. Again, our hint normally is u is generally the inside function. That would be our first guess, and see if we can adjust it. So u would equal 4t, du would equal 4 dt. I don't have a 4 dt, so I don't need the 4. So I'm going to cross it off from this side and put it on this side. So this is usually the steps I'm going to go through. I'm not going to do all of these steps that I did over here. Wherever there's a dt, I'm going to put a 1/4 du, and then this is e to the u. If you want to slide the 1/4 out front, that's totally okay. What's the antiderivative of e to the u du? E to the u. Ignore the constant. That's just a 1/4 out there, plus a c. So this is going to be 1/4 e to the 4t plus c. And again, we can quickly double check that. We're going to have the derivative of e to the 4t is going to be e to the 4t times 4. The 4 is going to cancel with the 1/4. That's going to leave us with just our integrand right there. And of course, the derivative of the constant is 0. Okay? All right. Easy enough? Okay. We did a problem just like this a couple days ago. Again, our only option there would be to cube this out, multiply through by the 28, and then integrate each one of the terms of the polynomial using the power rule, okay? Or the anti-power rule, if you want to call it that, okay? Now, I've got an inside right here. Let's see if we can do this using substitution. So u in this case would be 7x minus 2. The nice thing about choosing u to have a couple of terms, maybe one of them as a constant, is when you find the derivative of a constant, it's 0. So this is going to go from having 2 terms to just having 1 term. 7 dx. Okay, I kind of like to do it this way. I don't need a 7 dx, I need a 28 dx.
Yeah.
So times both sides by 4. So if instead of using this one, I use 4 du is equal to 28 dx, then wherever there's a 28 dx, I can put a 4 du. So here's what I'm going to write. I'm going to write a 4 du. Wherever there's a 7x minus 2, I'm going to put a u, so this is just 4u cubed du, which is very easy, because that's just the derivative of
U to the 4th.
u to the 4th.
Plus.
So this is 7x minus 2 raised to the 4th plus c, and there it is. So in this case, the constant actually goes away completely. Okay, and we've just got that power function right there. Any questions? Okay, so if you look ahead, that took about 25 minutes to introduce there. We've got a whole bunch of problems. All we're doing at this point is just practicing using the substitution technique, changing variables. We've got a whole page that we're going to do here, and we've got a bunch of hints. Hopefully, I'm hoping that I can get to the point where I can do a definite integral, but I think if you read this, you might be able to figure it out. I am going to finish this on Monday, so don't feel like you have to, well, you're not going to do any homework over the weekend anyway. Who am I kidding? Okay? All right, so let's take a look at this one. Now, I'll admit this one wouldn't be too terribly bad to just distribute through and then find the antiderivative of each one of the little power functions. That wouldn't be too difficult, but this is a good technique because if it was slightly more complicated, maybe with a higher power or something like that, this would really come in handy. So on this one right here, Is there a function that we can see its derivative or a constant multiple of its derivative in the integrand?
Yeah. Isn't
Which one?
W plus U the derivative of W squared plus 2W minus 3?
Yep, okay. So if I take these three terms and I made them u, the derivative of this would be 2w, and the derivative of this would be 2. Not exactly this right here, but pretty darn close. So here's our guess. Our guess is that u could be w squared, whoops, don't know what letter that was. Then du would be 2w plus 2 dw. Well, that is really close. I need a w plus 1, not a 2w plus 2, so what do? Okay, I'm going to factor out the 2, so I'm going to do du equals 2w plus 1 dw, and then I'll multiply both sides by a half. So I'll move that 2 to the other side by dividing by 2 or multiplying by a half. Everybody good there? So from that ugly mess, this stuff is u. This stuff is 1/2 of du, so I'm going to put a 1/2 out front and a du right there. Okay, careful here, because we still have a little bit of trickiness to get through. Increase the exponent by 1, divide by the new exponent. So my antiderivative is u squared over 4 plus c. Or if you wanted to write it as a 1/4 out front, u squared. So 1/4 u squared, so that's w squared plus 2w minus 3 raised to the second plus c. There's our antiderivative.
We can just leave it like that, right?
Yep. Okay, any questions there? Okay, let's take a look at the next one. Okay, and to some extent, when you're getting used to this, you do a little bit of guessing as to what u would be. I've tried to give you some good general hints, and we'll go over a couple more. Usually we choose u to be the inside function. Usually if we can choose it so it may have more than one term, one of which is a constant, okay, which will go away, that's helpful. So what do we think u would be in this case? Okay, so we'll do 4 theta minus 1. That means du is equal to 4 d theta, which I can deal with because the derivative of theta is d theta, give or take a constant multiple, right? Well, I don't need the 4 d theta, I just need a d theta. That's all I need to replace. So this is going to be 1/4 du is equal to d theta. So when I change variables here, this is what I've got. I've got the square root of u. Wherever there's a d theta, I'm putting a 1/4 du. So I've successfully changed into my new variable u, but this still doesn't look very good, so I probably ought to change forms again. Let's do this. Let's do 1/4 u to the 1/2 du. Then hopefully it's something that we can recognize. It's just a power. It's an ugly power. It's a 1/2, but the rule still applies. Increase the exponent by 1, divide by the new exponent. So if I increase 1/2 by 1, what do I get? I get 3/2. So this is going to be u to the 3/2. I don't divide by 3/2. I'd prefer to flip it over and multiply. So I'm going to multiply by 2/3. Still got that constant of 1/4 out there, plus a c. So I'm going to cancel here and here. So this is going to be 1/6 u to the 3/2 plus c. And now I just need to change back. So this would be 1/6 4 theta minus 1 to the 3/2 plus c. If you wanted to leave it like that, that would be okay. If you wanted to change this into 1/6, this would be the square root of 4 theta minus 1 cubed plus c. That would be okay too. Take either one of those. Any questions? Okay, let's take a look at this one then. So the chain rule, we call it the chain rule because you can see a function and its derivatives, just a big long chain of functions and their derivatives in the end result. We said we undo that using the substitution technique when you can see a function and its derivative or a constant multiple of its derivative in the integrand. So let's look at that for just a second. Can you see a function whose derivative also appears in the integrand? Yes, we can. What's our choice for u, or what's our first guess for u here?
1 plus y squared.
Okay, 1 plus y squared. For a couple of reasons. It's got that constant with it that will go away. And the derivative of y squared is 2y, which is a y with a constant, and we can deal with the constant. So du here would be 2y dy. Okay, there is my y dy. I don't need the 2. So I'm going to move that 2 on the other side. So I'm going to do 1/2 du equals y dy. So I'm going to change this into the integral of 1/2 du. And what do I write right here? 1 over u. 1 over u. Okay? Now, sometimes leaving that 1/2 inside there is a little bit dangerous. This might be a little bit easier to recognize if I put the 1/2 out front, 1 over u du. What is this? It's the derivative of ln, right? So its antiderivative is ln. Remember, we usually use the absolute value to guarantee we don't have any domain issues. So that's 1/2 plus c. So this would be 1/2 the ln of 1 plus y squared. Whoops. Need the absolute value there. Plus c.
I think we would need the absolute value for that one.
1 brings up, do we need the absolute value?
No.
Not on this one because it's 1 plus y squared. Okay? That's 1, and then we're going to be adding at the very smallest 0, so it's always positive. So we don't really need the absolute value. You may look in the back of the book and find this, though. What'd they do there?
They moved the power up.
Move the power up here using that power property of logarithms. 1/2 power would be the square root, so they may write it like that. Okay, so just keep that in mind. Okay, any questions?
Could we leave it like that though?
Sure. Yeah. So if that were a test question, I'd take this. Okay. If you look at, if this was a problem on an assignment, look in the back. It may be a little bit confusing, especially when they're trig functions or logarithms. Maybe they've manipulated it some way using some property or some identity. Good there? Okay. We'll keep going, get through as many of these as we can. I'm not going to do every single one of these completely. We're just going to do the substitution. What's our guess for u here?
T squared.
T squared. Du equals 2t dt. Okay, this is my personal preference. Okay, I like making this the right constant here. If you wanted to just do 1/2 and then just substitute here and then have it multiplied by 6 there, that's totally okay. It's going to end up being a 3 either way. I like doing this. If I need this to be a 6, I like timesing this side by 3 and timesing that side by 3. Okay? I just like that better, because then I can see that this is a 3 du is 6t dt. I can see exactly what I'm replacing. But again, personal preference. You do whatever makes it work for you. So this is going to be the integral of, well, wherever there's a 6t dt, I'm going to put a 3 du. So I just slap the constant in front and put the differential on the end. And then this is just e to the u. And then you can do that, right?
You just added 1.
What's the antiderivative? 3e to the u, right?
Plus c.
3e to the u plus c. And then all you have to do is just change the u back to a t. Good? Okay, now it gets a little bit interesting. So your hint is a U substitution or maybe another technique. Okay, because the cool thing about this is there are lots of different ways we can manipulate these, and maybe we can get the right answer multiple different ways. So this is in the section on U substitutions. Let's try this using a U substitution. Okay, I've got these two problems stacked on top of each other for a reason. They look very similar. They're very close, but they're done in very different ways. Okay, you want to find a function whose derivative also appears in the integrand. Usually it's the inside function. So if you look at this right here, the trouble with a sine and a cosine, the derivative of sine is cosine. Give or take a sine, right, a negative. Okay, and the derivative of cosine is sine. So which one should we choose?
Change it to secant tan.
We'll get there in a second. You're way too good at this.
Yeah, that's what I split up into secant.
Okay. All right. So, okay. So, if you want to do it that way first, okay. Let's break it into sine of x over cosine of x, 1 over cosine of x, dx. This is tangent of x, secant of x, dx.
Oh,
It's commutative, so this is the same as secant x, tangent x, dx. So what's its antiderivative? Secant of x plus c. There's the antiderivative. Okay? But you can't do that here. Okay? So let me show you how we do this. Okay? That's one technique. The other technique, and we can get the exact same answers, take a good look at this. This could be rewritten as the sine of x. And remember, when we square a trig function, it really means the cosine squared of x. So this is an inside function. So here's the problem. If you said, I'm going to say u equals the sine of x, okay, and I need you to pay attention because this is going to come up a couple more times, then du equals, it's true there's a cosine x and a dx, but look where it is. The cosine x dx, they're both in the numerator. They're both on the top. Where is the cosine x here? It's down in the denominator. You're not going to be able to move that. Okay? So that's the first issue. Okay? So if we let u equal cosine of x, not cosine squared in this case, then du equals sine of x dx. Both in the numerator right where we need them. So this is all set. Sine of x dx, du, cosine is going to be u, so that's u squared. Or u to the negative 2 du. Increase the exponent by 1, divide by the new exponent. So that's going to be negative 1 over u, right?
plus c.
Plus c. And u is cosine? So that'd be negative 1 over cosine x plus c. Negative secant. Let's see.
Yeah, that one, it's not the same sign. Well, if you're squaring it, it can be plus or minus cosine of x, right?
Well, gosh, this can be kind of tough. Does Maddie know what's going on?
Well, not on this, but I was gonna say, would it work if you, like, originally just substituted cosine squared for 1 minus sine squared?
There might be more than one way to do it, but this will work out. We're close to the right answer. Does anybody see the mistake?
Oh yeah, EU.
It's right here.
It's negative sign.
Oh,
Okay, so let me change colors. Remember I said once you start mixing sines and cosines, differentiating and integrating, it's easy to lose track. So there's a negative here. So there'd be a negative there. Negative here, negative here. That would make this positive. That makes that positive. That makes that positive. And there we go. Okay. Any questions?
Darn it.
Yep. Okay. Let's see. Let's do this one right here. And so we'll do this one and we'll do this one and then we'll call it good for today. You have a nice weekend. Okay. And then when we come back, we'll pick up right where we left off. You could do a couple of these. I mean, I would at least, I mean, it's going to be 5 days. I would at least look at integration by substitution. I'd at least look at a couple of them or review your notes before you come back. So let's take a look at this one right here because this one is different.
Kathy Nuttall to the front office as soon as possible. Kathy Nuttall to the office as soon as possible.
So this one, the hint is use substitution. There is no other technique on this one that I'm aware of. Okay, what we did before was we said, well, the denominator is cosine of theta squared, that quantity squared, and we let u equal just the cosine of theta. And the derivative of cosine of theta was, once we got it right, negative sine x in this case. Okay, I don't need a sine of theta. I need a sine of 2 theta. So on this problem, we're going to be a little bit tricky. We're going to say u equals cosine squared of theta. Or it would be better if we thought of this as the cosine of theta squared. Because then you can see how we're going to differentiate. We're going to differentiate using the chain rule. So that means du equals 2 cosine theta. Let's be careful on this one. What's the derivative of cosine theta?
Negative sign.
Negative, so I'm going to put a negative here and a sine of theta d theta.
So we're using the chain rule to undo the chain rule.
Yep. Okay. What about this guy right here? That doesn't show up. But does that look familiar?
Yeah, that's the double.
Okay, that's double angle. So du equals, this would be negative sine 2 theta. Whoops.
Yeah.
Sine 2 theta d theta. Okay, this right here is a double angle for sine.
Mm-hmm. But it's,
So
I guess we can move it over.
I don't need the negative, right?
Yeah,
So let's slide the negative over to the other side. So if I replace everything, I've got a negative du in place of sine 2 theta d theta. And wherever there's a cosine squared, I just put a u. So this is going to be a 1 on top and a u on the bottom. Is that okay? Antiderivative? Negative ln, absolute value u plus c.
Why is it negative? Oh, right, yeah.
Yeah, got that negative sitting out front. And let's see, so this is going to be negative ln of cosine squared theta plus c.
Since it's square, we don't need that absolute value.
Don't need that, okay? This would be okay if you don't want to put the absolute value. If you want to put parentheses there, that would be okay. What if you looked in the back and it said this?
Because of that negative.
Pulled that up there, negative exponent, did the reciprocal of cosine squared. Reciprocal of cosine squared would be secant squared. Okay. Okay. Any questions there?
Why would it be secant?
Because if you slide this up here, it would be a negative exponent. Negative exponent means reciprocal. Good. Okay. Any questions there? Okay, let's do this last one right here. So we've got the integral of ln of x quantity squared over x dx. And again, good hint there. It's usually the inside function, and can you see a function and its derivative in the integrand?
I say element of x.
Yeah, okay. So if we were to rewrite this, it would make it really clear. If we did the ln of x, quantity squared, times 1 over x dx, there it is sitting right there for us. Okay. Not only is it the inside function, but you can see its derivative in the integrand. So u would equal the ln of x, du equals 1 over x dx. So I get to replace this with du and that with u. So this is the integral of u squared du. So this is going to be u cubed over 3 plus c, which when we replace that, we're going to have the ln of x, quantity cubed over 3 plus c, and there's our answer. Okay?
If we bring that 3 down,
Stephen, if you could bring your program
Sure.
back to the
Mhm.
office at the
Well, wait just a second. Can we bring this down?
Thank you.
Can we bring that 3 down using the power property? Because it's the ln of x, it's that quantity cubed. It's not the ln of x cubed. Okay, so no, you can't. Good question, though. Okay, so let me just show you this before you leave. There's a hint on this one. A couple of these they're kind of tricky, okay, but they're very interesting and very good. Then there are a couple right here and on the top of the next page. These are not typical substitution problems. These are a little bit, well, this one's not too terribly bad, but these 3 problems right here, these are a little bit more advanced, and they're not things that you would just think of on your own, okay? But I think you could figure them out if you think about the fact that when we do a substitution, what we're doing is we're making a change of variables. We're making this equation, we're saying u equals this stuff, and then we're changing everything else into that variable, not only with the original equation, but any type of manipulation to that original equation, including finding the differentials or moving that u and x equation, or whatever it is, taking that u equation and moving things around to get what we want so we can replace everything, okay? So these problems, although they're a little bit on the tricky side, they're quite interesting, okay?
Even C,
What's that?
even C.
This one right here? You think?
I mean,
It looks so
kinda cute.
simple.
It does. It looks easy, doesn't it? Okay? Is that the end result of a differentiation formula, you know?
No.
No. And the only technique we've got to this point, the only additional technique we learn in this class is substitution. That one has to be able to be done using a substitution.
Yes, but
So the trick is figuring out, well, if I make u this, how could I change everything else into a function of u or a differential of u that is something that I can recognize and work with? Okay? It's not that bad. It's definitely easier than this one, I think. Okay? All right. Okay. Have a great weekend.